We present an efficient paradigm for planning feasible trajectories for the center of mass and the orientation of the body of legged robots. The idea of the work is to develop a 2D feasible region, which guarantees such feasibility whenever the projection of the center of mass lies inside it. The first step involves developing a feasible region guaranteeing dynamic balance and torque feasibility. Here, the feasible region is shown in gray, while the classical support region is represented by the dashed region. The black region is a scaled version of the feasible region used for planning. During the second step, we develop a reachable region, which guarantees the feasibility of the kinematic limits. Such region specifies the set of all possible center of mass locations that can be reached with a specified orientation without violating the joint kinematic limits. Note that a change in height of the center of mass or the orientation of the trunk can greatly affect the size, shape, and convexity of the reachable region. Finally, we can intersect the two regions that are defined on the same plane to get an improved feasible region. An efficient planning strategy is developed to ensure that the center of mass projection stays inside the feasible region. This simulation shows the high-Q robot descending a 30-degree slope while being attached to a rope to explore a low-height tunnel. The aim here is to assess the influence of an external wrench acting on the robot combined with the reduced trunk height necessary to walk in confined places. Due to the mentioned conditions, the feasible region tends to be very small in size and is shifted forward. We compare the center of mass planning strategy based on the feasible region with a stability planning approach developed in our previous work. Using the stable planning method, the planned target for the center of mass can be outside of the feasible region. As such, the whole body controller fails to achieve the desired ground reaction forces, and a tracking error of the center of mass trajectory follows. Using the feasible region, the feasible planning strategy corrects the target center of mass that was determined by the stable planning method. The strategy corrects the target to be inside the feasible region. To increase the robustness of the planning, a scaled version of the feasible region, shown in black, is used. We validate the feasible region and the center of mass planning strategy in a scenario similar to the simulation shown before. Here the Elingo robot is commanded to walk down a 45-degree ramp while constraining its center of mass height to 20 centimeters. A rope is attached to the robot and a counterweight is used. Elingo is used for safety reasons and the kinematic limits were virtually lowered. The feasible planning strategy successfully maintains the projection of the center of mass inside of the region, and no violations in the joint kinematic limits were detected. On the other hand, the stable planning target results in multiple violations of the limits. We also test the strategy on high Q while walking at an excessively reduced trunk height. The planning strategy again prevents the kinematic limits to be violated at such constrained configuration. We can also use the feasible region to plan the target orientation of the robot. This simulation involves a complex non-coplanar terrain that particularly challenges the kinematic limits of the robot. A typical planning method shown on the left is to align the orientation of the trunk with an estimate of the inclination of the terrain plane. While this can be effective on a lot of terrains, it might not be sufficient on very complex terrains. You can see here that one or more of the joints reach its kinematic limits. With the feasible planning strategy, these violations can be avoided as shown on the right. Due to the unoptimized orientation of the trunk when using the terrain-based approach, we can observe how the center of mass reaches the boundary of the feasible region and eventually violates the kinematic constraints. On the other hand, the feasible region on the right is adapted to fit the center of mass trajectory with the optimization of the orientation of the trunk. We also validate the feasible region for a trotting gait and dynamic motions using the Elingo robot. The feasible region becomes a segment and moves according to the acceleration of the center of mass. The projection of the center of mass follows the feasible region, inferring that dynamic stability is achieved.